Hello and welcome to my tutorial channel. This is the first lecture of quantum mechanics. I'm going to provide a comprehensive tutorial which includes many examples. The starting point is a review of four major domains of modern physics. We are already familiar with classical physics that describes the behavior of large-scale or microscopic objects. But in two extremes, the classical physics either is insufficient or to describe the natural phenomena, or it gives us incorrect results. One is at um, high speeds close to the speed of light, and the other one is at low dimensions comparable to the size of an atom, which is around 10 to the power of minus 9 or less. To describe the phenomena at high speeds, we apply the relativistic mechanics, which is introduced by Einstein. In low dimensions, when we deal with low speeds, much less than the speed of light, we apply the quantum mechanics. And finally, when we deal with microscopic or low dimensional objects at very high speeds, we use the quantum field theory, which is beyond this course. One thing that I should emphasize is that there is not a sharp or clear border between these domains. For example, at some dimensions like 10 to the power of minus 6 meter, we may observe some quantum features, but the classical physics is still good enough. The other thing I should highlight is that in this course we mostly deal with single particle and at most two particle systems. If we have many particles, in that case we should either use statistical mechanics or many particle theory. But in this course we mostly deal with single and two particle systems. Now let's start our discussion by one simple example. Consider one object or particle with mass m moving along x direction. The specified force F of x and t is exerted on the particle. The goal of classical physics is to obtain the position of the particle as a function of time. Once we get x of t, we can obtain all favorite dynamical variables. For example, if I take the derivative of with respect to time, I get the velocity, and then I can obtain the momentum, which is m times v, or kinetic energy, which is 1/2 of mv squared. We have two approaches or three approaches to find the x as a function of time. One is Newton's second law, which is F is m d squared x over dt squared, or also we can use Lagrange or Hamilton formalisms, but all these approaches give the same result. For microscopic system or low dimensional systems, we only deal with conservative forces. So for those forces, we can define a potential energy, and in that case, we can simplify the Newton equation like this. F is m d squared x over dt squared, which is minus partial derivative of the potential energy with respect to x. We can generalize this equation to higher dimensions as well. This is a partial differential equation, so when we have the initial conditions, for example, x at t equals to 0 or dx over dt at t equals to 0, we can solve this partial differential equation and obtain x as a function of time. But the approach of quantum mechanics is totally different. In quantum mechanics, we have wave particles. So some objects like electrons sometimes demonstrate wave-like properties and sometimes they show particle-like properties. So we call these things wave particle because depending on the situation they may demonstrate either wave-like or particle-like features. Schrodinger introduced an equation that is suitable for describing these wave particles. That equation introduces a new function, we call it wave function. We show it by letter psi, which is a function of x and t in one dimension, and in three dimension, of course, it will depend on r and t. In this lecture, I only introduced the Schrodinger equation, which is I h bar partial derivative of psi with respect to time is equal to minus h bar 2 divided by 2m partial derivative of psi squared divided by x squared plus v psi. In this equation, I is the square root of minus 1 and h bar is the Planck constant divided by 2 pi, which is 1.05 times 10 to the power of minus 34 joule second. If we have the initial wave function at t equals to 0, we can in principle solve the Schrodinger equation and obtain the wave function at later times or in the future. This is very similar to the Newton law that gives us x of t once we have x of 0 or dx over dt at t equals to 0. But there is a big difference between these two. This is deterministic, which tells us that once we have this function, we can determine the position of the particle for sure in all future times. But the wave function is something different. We will discuss its physical interpretation in the next sessions. Also, in the next lecture, I'm going to discuss how to obtain the Schrodinger equation. In fact, we don't have any mathematical proof for obtaining the Schrodinger equation, but there are some guidelines that help us to find the Schrodinger equation. The interpretation of the wave function is a bit tricky, and I will discuss that in the next lesson.